Welcome back to SSD. Now we are going to continue with the design of the beam element after having undertaken the superpositioning successfully. I am now back to SSD and working on the model called ptc_bridge.sofistic, which can be found on your desktop in the subfolder named ptc_bridge. However, this file can also be found in the corresponding model file folder of this chapter. Please right-click on the task CSM Bridge Design Superpositioning and choose the Insert Task option from the drop-down list. The Insert New Task dialog box will be open for you, and please choose the CSM Bridge Design Beams from the list and then click on the OK button. If you double-click on the newly created graphical task, it will open and we are going to find two tabs in it. On the first one, we can choose which checks, or design checks I should say, would be performed on the beam elements, such as the ultimate limit state check, the crack control of the beam elements, stress limitation, decompression check, and stress strain check. Whenever you select design check, the corresponding chapter will be named for you in the description below. For example, the crack control will perform a design check where the minimum reinforcement check under the characteristic rare combination according to the Eurocode 1992-2005 chapter 7.3.2 will be performed. And parallel to this, a crack width check under the relevant combinations according to the Eurocode 1992-2005 7.3.4 will be performed. Similarly, in the following design checks, a description and a chapter can be found for better orientation and understanding the design procedure behind this task. If we did perform all of these checks, our output in the report browser would be very extensive and difficult to follow. So what I suggest is to either perform one of these design check for one time and then reinsert this graphical task in the SSD task tree and perform the remainder of the design checks. However, before start any of these design checks, my recommended workflow would be to uncheck all of these design checks and go to the second tab, which is the Check Print tab, and within this tab one or two beam elements to be chosen for the detailed output of linear stresses under the characteristic, the frequent, the quasi-permanent and the ULS design combination. Apart from calculating and presenting the linear stresses of the selected beams, a detailed output of the design procedure in the ultimate limit state will be performed on the selected beam elements as well. And finally, a detailed output will be presented for the crack width check under the relevant combinations according to EN 1992-2005 chapter 7.3.4. So let's select quickly two elements, beam elements in our system and perform the check print on those. I will just simply click on the plus sign and then I will click on the system visualization to select the beams. The system visualization will be open for me and I will choose this beam element and one beam element at the support, and then I will click with my right mouse button and choose the Finish Selection option. If I do so, I will be directed back to the original interface, and here I would like to simply just a little bit widen these columns, and basically I'm just going to inquire the results, the stresses and the checks at the start of the beam element to even reduce the output amount. Now of course, if we clicked on the OK button, then this task would be performed or executed. However, I would like to show the underlying text input, so please take out the Process Immediately checkbox and then click on the OK button. In this way, the settings will be stored, and by clicking with our right mouse button and choosing the text editor option from the drop-down list, We can review the corresponding text input, which as you can see performed in module CSM. And again we are generating a new file with the extension _38 file, and with the help of command apply we perform or execute this file. In the next two command lines, with the help of command SLS, we are selecting our two beam elements, and then we perform the check print on them with the command daisy check. E-type beam means that we would like to perform this check print on beam elements and not on quad elements. Before we run this CSM input, I would like you to rename this task. So come back to the SSD task tree, right click on the task and choose the rename option. And now I will simply right click on the task and choose the calculate CSM bridge design check print of selected elements. Now the task will be performed and we can have a look at the output, but also the input of this newly created file. Now the analysis has run through, so let's continue by overviewing the results of this task in the report browser in the next video. In this video we are going to look at the results of the check prints of the selected elements in the report browser. Please right-click on the task we have just analyzed and choose the reports from the drop-down list. Go to the Results tab and select the first entry and choose the Collapse All from the drop-down list. Now please click on the main title line and open up the chapters and choose the first AQB. Simply clicking on it, the output of this module will be presented. Here we will find the used design code, and if we open up the current AQB module, the other chapters will be visible, such as the used materials, for example, or the selected beam elements. Then we can find the considered load cases in a table format. In this table the first column is about the load case number, then the second one is about the action this load case was assigned to. The third column shows the part of the cross-section on which this action and the load case was acting. For example, we will find first the load cases that were acting on the gross cross-section, such as the load case 31, the wind load, or 51, the settlement loads, or T, the temperature loads, or load case from 101 all the way down to 312, which were from the traffic loader task, and they were also acting on the gross cross-section, the final cross-section. Then we will find all the pre-superimposed result load case starting from 1141 and assigned to action y_1, and we can follow along the load case numbering for the other actions such as y_3, 4, 8, 9, the y_D, the y_G for the fatigue analysis, and then we will find the load cases that were not acting on the final gross cross-section because they were stored during the CSM analysis, and therefore they are containing the G, P and the C part of the combinations. And here you can also read the action that they are assigned to, but as you can see, the cross-section part is always according to the construction stage. Here, for example, the load case 5010 assigned to action G_1, the cross-section part that this load case is acting on is the cross-section that was assigned in the construction stage 10. And so on and so forth. You can see the changing of the cross-section and the corresponding GPC load cases in the table below. Then in the next column we can always see the designation or the title of the load case, and finally in the last columns we can see the unfavorable, favorable safety factors and the combination factors. In the last column, finally, we can see the behavior rule of the load case within the action. After the considered load cases table, we will find the elastic stress check. And this part of the output is exactly the same as we saw in the explanation video of the CSM check print output. Here we can see first the stresses, the maximum and minimum stresses in the system from the considered combinations based upon the used material. So first we can find material number 1, which is the concrete, then we will find material number 2, which is the reinforcing steel material, and finally the maximum and minimum longitudinal stresses can be seen in the tendon material. I have already provided a detailed explanation for the forthcoming tables, which can be found in chapter 10 and called Report Browser Output with Check Print. In the aforementioned previous video, I have already explained the content of the table cross-section, the selected stress locations, and the tendons. So now I'm just simply going to skip the explanation of these tables and start the introduction of the normal stresses table. This is very similar again what we saw in the check print of the normal CSM. However, here we can find the results load case wise, or I should say actions wise. As you may remember from the CSM, normal CSM check print, we have two tables, normal stresses table 1 and normal stresses table 2. This is because we do not have enough place on the A4 paper to print the third tendon results as well. So if we look at the considered load cases and the calculated normal stresses, we will see that now the results are detailed according to the actions. First we can see the results from action G_1, then from action G_2, then the effect from the overall G. So if we add up together the 4,866.5 kilonewton meter and the 790.3 kilonewton meter, then we are going to get this 5,656.8 kilonewton meter. Similarly, we can see the stresses from action P, the pre-stress. In this case, we can even found a test line where the primary and the secondary effects are added together, and we can see that the results are really the same as we just reviewed the normal stresses from the overall pre-stress action. Then we can find the results from action C_1, which is the creep and shrinkage effects until the traffic opening. Also we'll find C_2, which contains the effect of the creep and shrinkage from the traffic opening until time infinite. And in the next line, these two effects are added together or superimposed. This part of the table contains the G, P, and C effects of the combination rules. These internal forces and the stresses in the stress points will be used to combine together or superimpose them with the effects arising from the actions that are acting on the final cross-section. So in the table now we are going to find two blocks. The first block contains the actions, the results from the actions that were set up to get the maximum my bending moment in the selected beam elements. The second block contains the variable actions that are acting on the final cross-section, but in this case the combinations were undertaken in such a way to get the minimum my bending moment in the beam elements. And again we will find the normal forces and the stresses within the cross-section. The variable actions that we are considering in these two blocks are the gr_t, u, and 2, then all of the containers or actions from the pre-superpositioning, such as y_1, 3, 4, 8, 9, action y_d, and Y_G for the fatigue design. If we scroll down in the output, then we are going to find some special combinations, from which the most important one is the GPC effect together. So a special combination was created to calculate the internal stresses from the total G, P and C effects. If we have the result of this special combination, we can simply superimpose the effects from the pre-superposition combinations. And this is the way how we can obtain the results, for example, from the rare combination rule, where we are looking for the maximum extremum for the my bending moment, and then also the minimum extremum from the my bending moment. In a very similar manner, the frequent combination rule can be set up, and the positive extremum for the my bending moment can be extracted or obtained, and also for the negative extremum. The other important combinations that needs to be created for the design checks are the permanent one, another permanent for the decompression check, and finally a combination for the ULS design. Of course, the very same output is available for the other selected beam, the 200,035, which I'm not going to explain in detail since it is the same as for the previous beam element. Instead, I'm going to click on the next entry line, which is a photo, or a picture I should say, that describes how the stresses in the important combinations such as rare, frequent and permanent are plotted. Since this is what I have just explained with the help of the tables, this picture provides us only one important information, namely that the stresses of the important combinations are plotted below with the help of module results. And really, if we click on the graphics tab, we can see nice pictures about the stress distribution along the local z-axis, which we are going to review in a later video. However, now let's go back to the results tab and continue with the explanation of the output of the ULS design in the next video. In this video, I try to explain about the output of the ULS design. As you can see, I have already selected the module AQB Check Print-ULS design. We can find information again about the used materials, the selected beam elements, and then an information about the reinforcement, which will be accounted for sectional values with a factor of 1.0. This means that during the analysis, the minimum amount of reinforcement will be used as a base reinforcement that we had been defined at the cross-section definition. The amount of reinforcement will be enhanced upon request to fulfill the ULS criteria. Then we can see an information about the reinforcement saving, which will happen into the design case number 91. You need to know that the amount of reinforcement, the necessary amount of reinforcement, is stored in so-called design cases. Somehow we need to identify the reinforcement distribution, therefore we give them numbers. Normally, if you perform a ULS check and assess the amount of reinforcement, it is going to be stored in reinforcement distribution number 11, or we can also say design case 11. Then if you perform the SLS check, the amount of necessary reinforcement will be stored, for example, in design case 12. And so on and so forth. So every design check is going to generate a design case where the necessary amount of reinforcement is stored. Finally, from these distributions, an envelope will be created and the necessary amount of reinforcement with the maximum values will be stored in design case number 1. However, this is not the case with the check print of selected elements, In this case, module CSM creates a new design case with number 91, as you can see, and store the necessary amount of reinforcement. So this design case number 91 is not going to conflict any of the forthcoming design cases. If we scroll down a little bit in the report browser, we are going to find the Consider Load Cases table once more, in which the load cases that are acting on the final gross cross-section presented at the very beginning. However, when we scroll down the table, we will find also the load cases that are acting during the construction stages, starting with 5010. If we now open up the design for the ultimate loads, we are going to see the safety factors and the strain limits that are being used in the ULS checks. In the next table, you can find the parameters for the reinforcement, such as the amount of minimum reinforcement for beams or for columns. The amount of maximum reinforcement, for example, it is also presented. And then we can see some statements regarding the ULS design. For example, it is stated that the tensile force in the longitudinal reinforcement due to shear are not accounted for. This means that the so-called shift rule is not accounted for in this ULS check. This is the default setting in the analysis, and you need to be aware of it, because at the end of the design procedure, when you are creating the reinforcement drawings, you must make sure that the reinforcement is longer to account for the tensile forces in the longitudinal reinforcement due to shear. The other statement is that the longitudinal tensile force from the torsion is going to be considered, and the exact formula is presented. This formula results an additional longitudinal normal force, which will be considered in the calculation or analysis of the necessary amount of reinforcement in the ULS state. Then it is also clarified that the safety factors for the material of the cross-section and the material of the reinforcement are considered. In the next table, we are going to see the properties of the applied materials, such as the safety factors, the maximum compressive strengths, the corresponding strain, the maximum tensile stress and its corresponding strain, and they are all plotted material-wise. Then the printout will continue and presents the design forces and moments, but first it shows the combination of load cases. If we look at this, we will see that in load case 2100-05, a ULS combination for the positive extrema will be created, in which the action G, P, C will be considered with the corresponding safety factors, plus the content of the pre-superimposed container for the ULS design case, the Y_D. And a similar combination has been generated for the negative extrema. In the design forces and moments table, we will find, for example, this positive max extremum, such as the my bending moment, which is equal with 16,898 kilonewton meter. And we can also review how this value was calculated. The contributing load cases are mentioned in the table with the corresponding safety factors. We can find, for example, load case 5010 with a factor of 1.35, load case 5020 with a factor of 1.35. Then after the 5000 load cases, we can see the 6000 load cases, which contains the creep and shrinkage effects from the various construction stages. And finally, we will find the governing load case from the Y_D container. In this case, it was a load case 2141 with a factor of 1.0. And if we sum up these load cases with the factors, we are going to get this maximum my bending moment. The minimum my bending moment has been generated and stored in load case 2100-06, and it was calculated within the very similar fashion. The maximum and minimum MY bending moment values were calculated at the beam beginning and at the beam end, and similarly they were also assessed for the second selected beam, also at the beginning of the beam element and at the end of the beam element. In the footing of this table we are going to find three very important statements again. The first one is about the longitudinal tensile force being considered, as we already discussed. However, the second and the third statements are new information for us, and they are stating that the forces and the moments do not contain the statically determined part of pre-stressing and eigenstresses, and that the forces and the moments are referred to the total section as defined in the Aqua module. The first statement means the following. If you look at the output, you can see that we do not have any normal force in our beam element, although we considered pre-stressing. How could it be? The fact is that we only considered the secondary part of the pre-stressing and also of the creep and shrinkage effects. From the primary part of the pre-stressing and the eigenstresses, we do not have any stresses or internal forces. However, since our structure is statically indeterminate, the secondary effects of the pre-stressing and the creep and shrinkage effects are causing additional internal forces, and they are considered when we are calculating, for example, the maximum MY bending moment in our beam element, but only the secondary part of these internal stresses. At this point, it's worth giving some additional information about the consideration of the pre-stress in the ULS design procedure. Because what SOFiSTiK does is that excludes the pre-stressing when we are calculating the internal forces of the cross-section, and we consider the pre-stress on the resistance side of the equation, in a way that we specify the pre-stressing steel with an appropriate initial strain. And during the iteration procedure, when we are looking for the balance of our cross-section, this initial strain from the pre-stress will be considered. And also, as it is stated in the third statement, the forces and moments are referred to the total section as they were defined in Module Aqua at the beginning. The next chapter to review in the output is the required reinforcement table. This table delivers a lot of important information for us, such as the strain distribution in our cross-section, or the required reinforcement per layer, and the relative capacity of the cross-section. The way how you should review the results and the content of this table is that you can distinguish between different colors, or I should say lines with different background. You can see lines with white background and other lines with dark gray background, and the corresponding lines in the output, in the results, do have the same background color. Now let's look at together, for example, beam element 200,017 at x0. The assigned cross-section is 101, which means it is an interpolated cross-section. And the load case we are looking at now is 2100.05. I have increased the size of the page in order to better read the numbers in this table. And what we can see in this table is the NRD, MYRD and MZRD are 0, 16,878 and 0 respectively. The values NRD, MYRD and MZRD are the capacity of the cross-section respectively. Now I will split my screen to be able to represent the acting external force and the capacity of the cross-section. If I hit the Ctrl and space bar, the screen will be splitted horizontally. In the top part, I'm going to go back to the internal forces of a beam element 200,050 x0 and load case 2100.05. And for the bottom part, I'm going to show you the capacity in this table. what you can see is that in the design forces and moments, the maximum MY bending moment was 16,879.8 kilonewton meter. And in the capacity, we also find the very same value. How could it be? Is it just a coincidence? No, actually we can also see that the relative capacity is 1.00. So what happens internally is that the software increased the reinforcement amount in layer number 1, which was the bottom reinforcement layer, and the increasement was undertaken until we reached the capacity of the cross-section being equal with the external force. So basically the internal criteria is to increase the reinforcement until we reach the capacity of the cross-section being equal with the acting external force. And what we can see in this case is that in the top layer, in the left layer, in the right layer, also in the torsional reinforcement layer, the minimum amount of reinforcement that we had defined was kept and used. Only the reinforcement in the bottom layer had to increase to fulfill this criteria. One additional information is that layer Z is referring to the area of the tendon. In the highlighted line, we also receive information so-called epsilon 1 and epsilon 2. These are the strains in the outermost fibers of the cross-section. On the compressed part it is minus 2.62 promille, and in the tensile part it is 20 promille. We can also find the corresponding safety factors for the materials being equal with 1.5 for the concrete and 1.15 for the reinforcing steel. In the light gray line we can find a value for the delta VZI, which is basically the change in the vertical shear force, and it is due to the inclined tendon. As we discussed, the tendon in this beam element is not exactly horizontal but a little bit inclined, so from this inclination we are going to get some change in the vertical shear force. The next two values that are presented in the table are the YN and the ZN respectively. We can find YN is 0 and the ZN is 139 mm. The YN and the ZN values are the coordinates of the zero strain line in the cross-section. Let me show you it in a small picture. If I switch to the result viewer, I can represent the linear stresses in the cross-section, and as you can see at the bottom I have the tension, and at the top of the cross-section I have the compression. And this value 139 is measured from the origin of our coordinate system of the cross-section, and the 139 mm is roughly somewhere here, where the linear strain diagram change its sign. So from the compression it comes down to 0 and then it starts to increase, and the location when it goes to 0 is the coordinate Zn. Then the next two outputs are the E plus and the E minus in millimeter. They are giving the location of the resultant of the tensile forces in the cross-section and the location of the resultant of the compression forces in the cross-section. And they are measured from the center of the gravity of the cross-section. Please notice, if you subtract the minus 433 from the 673.3, you are going to add up with the 1106.7 mm, which is the lever arm of the cross-section, and it is titled with Z. This value of Z will be used later on in the shear design. In the lines which are marked with dark gray color, we will find the epsilon values and the corresponding sigma values, and they are listed material wise, as you can see. So if I select the first line, I will have some information about material number 1, which is the concrete. 1.13 promille is the epsilon null. which is the strain in the center of gravity of the cross section. So in this case it means that we have a little bit of tension in the center of gravity. In the topmost fiber we have minus 2.62 promille, and in the bottommost fiber we have 20.94 promille in the concrete. We will find the corresponding sigma stress in the concrete being equal with minus 22.7 megapascal, and of course the concrete cannot handle the tensile strain, so the stress in the concrete will be equal with 0. In the top reinforcement layer, which is layer number 2, the strain in the rebars is equal with minus 1.68 promille, and the strain in the bottom reinforcement layer is equal with 20 promille, which is the limit. And the corresponding sigma stresses is, as you can see, minus 336 in the compression reinforcement, and we will find the stress in the tensile reinforcement being equal with 447.8 megapascal. Since the reinforcement in the top fiber is a little bit closer to the center of gravity, therefore it is reasonable that the strain is smaller than at the top fiber of the cross section. Also, it is reasonable if we have 20 promille strain in the bottom reinforcement layer, then in the bottommost fiber in the concrete we are going to have a little bit bigger strain, since there is roughly 5 cm between the reinforcement and the bottommost fiber. For the tendons, we can see the strains are equal with 20 promille, and we will find the corresponding stresses in the tendon. The next 3 lines showing the stresses within the tendon one by one, so in tendon 1, 2 and 3, and we will see and find a sigma min and sigma max value. The sigma min value is the stress value in the tendon right after the grouting. And also we are going to have some extra sigma stresses due to the variable action loads. Of course, all the aforementioned results are listed at the other end of the beam element, and also it is available and printed for the other selected beam element, beginning point and end point. Finally, at the footing of the table we are going to find the legend. So here you can have an overview about the values presented in the table one by one in detail. I would like to call your attention that sometimes next to the values you will find a superscript, for example with 1 and 2. If you see such a superscript next to a value, here you can read the meaning of that superscript. Now I'm going to finish splitting my screen again with the Ctrl space button, and I'm going to click on the shear design, which I'm going to explain a little bit about. First, in this table we are going to find the design values of the materials. For example, in line 1, the concrete material, we can see the FCD value, the tau RD value, sigma CV, sigma CT value, and the sigma CV plus T value. FCD is the design strength of the concrete, the tau RD is the design value of the shear capacity of the concrete, sigma CV is the maximum allowable compressive stress for transverse shear. From these two we are going to get the maximum allowable compressive stress. In regards of the structural steel and the tendon, we are going to find the design strengths of transverse reinforcement. This means that the shear links or the necessary amount of shear reinforcement will be calculated based upon the properties of material 2 and 3. If you may remember, we have created a special material, material number 3, specially for the design of the shear links. Below the table we can find some information about the tangent of the inclination of the compressive strut, considered between the values of 0.40 and 1.0. And also we can find the tolerance for the iterations, how much the exceedance of the shear or the principal compression stress could be. Then if we scroll down the table, we will find the required shear reinforcement table. That gives us a lot of information about the shear design. First, as usual, it starts with the number of the beam, then the location of the cross-section along the beam, finally the cross-section that had been assigned to this beam element, the investigated load case, and in the next column we can see the name or identification of the shear cuts. We have defined these shear cuts at the definition of the cross-section, so let me just simply refresh the names and the location of these shear cuts with the help of a picture of Result Viewer. So if I go back to SSD and click on the Results button, the Result Viewer will be open, which I'm going to explain a little bit later in our course. However, right at the opening of Result Viewer, I can see a cross-section overview with the shear cuts also presented in it. So if we look at it, we can see that the Web 2 shear cut was defined here, the Web 1 W1 was defined here, the FLR, which stands for flange right, was defined at this location. Now going back to the report browser, we can better orientate ourselves. So now we know, for example, that the W1 shear cut is the lower shear cut of the web. The W2 is the upper shear cut, roughly at the center of gravity through the web. FLR is the shear cut in the flange on the right side, and FLL is the shear cut in the flange on the left side. Now I would like to clarify why we can see two values for the cut 1, so the web cut 1 and web cut 2. Basically, the way how we define these web cuts were in the cross-section editor, and we instructed the software to create a shear cut through a web. So not a shear cut through a flange of the cross-section, but through the web. In this case, the software automatically split the shear cut into two parts, and the reason behind is that together with the vertical shear force we also have torsion in the cross-section, and the torsion can increase or decrease the effect of the vertical shear force, and its sign could change within one cut through the web. Let me show you an example. Now I'm presenting our cross-section, and what you can see on the screen is the shear flow from 1 unit torsional bending moment. And if you try to imagine, our cut V1 is somewhere here, so it is very important that at the beginning of the cut the shear stress is acting in the vertical direction downwards, whereas the second part of the shear cut, the shear stress is acting upwards. As you can see, the sign of the shear stress from the torsional bending moment can increase or decrease the effect from the vertical shear force. If we look at the shear stress from the vertical shear force, we can see that the shear stress acting downwards. So that is why it is very important that internally the cut is going to be divided into two parts, the beginning part of the shear cut and the end part of the shear cut. And this is the reason why we can see two lines for every cut that had been generated as a web cut in the cross-section editor. What we can see in the next column is the shear flow in kilonewton per meter unit. It was calculated by dividing the design shear force with the lever arm, which is the Z in millimeter. And if you divide this with the half length of the total shear cut, which is in this case 1100 millimeter, finally you are going to get the shear stress in the first half or the second half of the shear cut. From the given output, it can be seen that the shear stress from the torsion is in equilibrium. Therefore, we are getting the very same 0.17 megapascal shear stress in both parts of the cut. The shear stress from the torsion is 0, as I mentioned, and the value of sigma 2, which is the compressive stress of the concrete, is also 0. This is due to the fact that the shear stress is very small. We can also see it from the required shear reinforcement amount, which is equal with the minimum, and also we can find a superscript next to the minimum amount of reinforcement value. In other words, we do not need to use any special reinforcement, shear reinforcement. The minimum amount is enough. Now if we review the remainder two shear cuts within our cross-section, the FLR and the FLL, we can see that they are only consist of one part, because the output contains one line per flange cut. This is because we had defined these type of cuts in a different way in the cross-section editor. We instructed the software to create a flange cut and not a web cut, because in this case the calculation of the shear stress is different from the web cut. In this picture from the AQB theoretical principles, I would like to show you how the shear flow is calculated if we define a flange cut. Basically, the software integrates the normal force along the cutted area at the beginning of the beam and also at the end of the beam. The normal force on this diagram can be seen with the FD, and at the end FD plus delta FD. The software will take this delta FD value and will divide it with the length of the beam element. This is how you are going to get the shear flow in the cut. And if you divide this shear flow with the length of the shear cut, you are going to get the shear stress in the cut. This is what you can see, for example, in this line, flange right, and you can see this plus dF, which tries to refer to the method that had been used to assess the amount of necessary shear reinforcement. So if you see the plus dF, that you can be sure that the difference of the normal forces will be used to assess the necessary shear reinforcement. However, if you can see a value at the lever arm, then you know that the previously explained method was used to calculate the shear stress in the shear cut. The method to be used is automatically selected by AQB. Sometimes you will find a very special input for the lever arm, like for example in this case 80% times E. E refers to the reduced elastic stresses. And let me try to explain what this 80% refers to. In the presented picture you can see the two states of the concrete cross-section, state number 1, the uncracked, and state 2, the cracked one. In the second case, the cracked case, the shear flow can be calculated as the shear force divided by the lever arm. However, when we have an uncracked section, so the cross section is in state 1, then the shear flow could be calculated as T multiplied with the SY value and divided by the IY value. So T times S divided by I, and if state 1 is more unfavorable than state 2, then the shear flow from state number 1 will be used. However, a further reduction will be used, namely a stiffness reduction of the cross-section, and the amount of this reduction is the ratio between the lever arm in the first state and the lever arm of the second state. And this is what the 80% times E tries to refer to. Of course, the same output is applicable for the other end of the beam element and for the other selected beam element as well. And again, in the legend of this required shear reinforcement table, we will find a brief information about the used terms and letters. If I click on the Check Print-ULS design, you will see a small picture which tries to explain what I went through in this video. Okay, so this concludes the check print of the ULS design, and let's continue with the review of the check print of the crack design in the next video. In this video we are going to review together the check print of the crack design. The output is very similar what we already get used to. First, we can see some information about the used material in this design. And then we can see again the selected beam elements. It is important to notice that the reinforcement will be again saved to the very same design case number 91. This means that the previously calculated reinforcement will be overwritten. It seems to be strange, but since it is just a check print, and this task was inserted only to review the first results of the selected elements, therefore it is not a problem if the reinforcement amount that had been calculated in the ULS checks is now being overwritten by the crack design. When we will perform the real design of the beam elements, a separate reinforcement distribution will be provided for every type of checks. Again, we are going to find the considered load cases, which will be superimposed for this crack design. The table is very similar what we already discussed, so I'm not going to explain it now in detail. We already did it. So after this table, finally we are going to reach the nonlinear stresses chapter, where we can read the parameters of the nonlinear stresses. It is important that the design code is mentioned according to the crack width check will be performed. The minimum and maximum value of the effective zone is also described. Then we can see information about the crack width, which is set to 0.2 mm in this case. Finally, it is stated that both of the materials in the cross-section will follow the serviceability stress-strain curve, without the safety factor being applied. In the below table, we can see the properties of the applied materials. And then if we scroll further down, we will find ourselves in the nonlinear stresses table. The previously mentioned color code is also applicable in this table. We can see white background, light gray background, and dark gray background. The coloring of the headlines will match the coloring with the result lines. So what we can see in this table is that first we examine beam number 200,017 at x0, so at the beginning the cross-section 101 was assigned to this beam element, and we are looking at the results of load case 9395. The next three values are the NI, MYI and MZI values. These are the internal forces in our cross-section, or we can say also the integrals of the nonlinear stresses in our cross-section. Please notice that we have a value at the Ni, which means that the tendon stresses are included in the cross-section. And really, if we multiply the sigma t, which is the tendon stress, with 3, since we have 3 tendons in the cross-section, we are going to receive this 4,400 kilonewton. The next two values are the Yn and the Zn. These values are showing to us the intersection of the neutral axis from the origin of the coordinate system, of the local coordinate system. Then we will find in pairs the sigma min and sigma max values, first for the concrete. In compression it's minus 45.2 megapascal, however in tension it is 0 because the concrete has cracked. Then the sigma minimum and sigma max stress in the reinforcing steel material. And finally the sigma minimum and sigma maximum stress in the tendons. Then you will see two values, one for the EY effective and one for the EZ effective. These values are presented in megapascal, and as you can see, the EY effective value is a small value, so it means, or it indicates, that the cross-section has cracked. The corresponding strain in the centroid epsilon null and the curvature kappa y is also presented in the table. However, as you can see, there is no third line which is standing for the H, the D and the crack width itself. The reason behind is that first, the software tries to fulfill the crack width criteria with the amount of the minimum reinforcement in the cross-section. If it is satisfactory, then the crack width is presented at the third line at W. If we cannot find a third line, it means that the crack width check was not satisfactory and the amount of the minimum reinforcement needs to be increased to fulfill the crack width criteria. And this is what we are going to find in the next three lines with the same load case number. The NI, the MYI, the MZI values are the same, but the other values have changed. And now we receive the third line stating that the crack width is really 0.2 millimeter with a corresponding increased amount of reinforcement being equal with 182.9 centimeters square. The stress of the reinforcing steel is presented in the table, and also the stress in the reinforcing steel at the initial crack is presented as sigma SR with the corresponding H value and with the used diameter. Please notice that we used reinforcement bar with a diameter of 16 mm in the bottom layer. Then how could it be that we see 15.1 mm here? The reason behind is that all the reinforcement bars that are contribute resistance against the vertical bending moment and falls within the tensile zone will be considered, and the weighted diameter of these bars will be presented here at D. Maybe the best is to illustrate it in the cross-section view. So the height of the tensile zone is 240 mm, which is roughly about here. And in this picture I am presenting the diameter of the rebars. So as you can see, diameter 10, 8 and 16 bars will be involved in the analysis of this D value according to a weighted procedure. Then in the next three lines we will still see the beam 200,017 at X0, but the crack width check is now being performed on the minimum MY load case, which is 9,396. And in this case, as you can see, the NI value in the cross-section is the same. However, the MYI is a much smaller value. Hence, the height of the tensile zone has been changed. Also, the considered reinforcement in the tensile zone is greater than previously was. The stress in the reinforcing steel is only 20.5 megapascal. And the crack width is only 0.03 millimeter. For the second selected beam elements, we can see there is no problem for the load case of the maximum MY bending moment. Here, the software could find the necessary amount of reinforcement to fulfill the 0.2 millimeter crack width criteria, with quite a reasonable stress in the reinforcing steel. However, for the minimum MY bending moment, the strains in the centroid and the curvature of the cross-section shows an infinitely high number. This means that the iterative procedure in module AQB was not successful. In the last three lines, we can see that finally the software found the equilibrium, however with a very high amount of necessary reinforcement. This indicates that we should provide more tendons in our system to be able to provide a higher NY value in the cross-section. And this is exactly what we are going to do in the next video. Before we jump into the real design of the beam elements, of all the beam elements in the system, to make a more economical design. In this video, I'm going to revise the model and introduce more tendons to the system to provide a more economical design of the reinforcement in the structure. So I headed back to SSD, and from SSD now I'm going to open SOFi Plus to revise the model. After the SOFi Plus having opened, I'm just going to revise first the pre-stressing system. So on the system tab I will choose a pre-stressing system and double click on the already created pre-stressing system number 1. First I'm going to make a slight increase of the number of the strands from 12 to 15. Then I'm going to click in the line called nominal force per tendon, and on the very right side of this line I'm going to click to update the value of the pre-stressing force. Now it is changed to 2509.6 kilonewton, and I will leave the dialog box with the OK button. Now I'm going to click on the pre-stressing tab, and I will right click on the tendon geometry axis _1 and choose the Edit with PT Editor option from the drop-down list. I will be directed back to the PT Editor, and there I'm going to choose the Edit Geometry tab. Here what I would like to change is the location of the tendon at the middle support, so I will select the span station number 2, and also I will just slightly change the V value to be equal with 0.1 meter, and then I will click outside the table. Basically I just reposition the tendon at the middle support to a more extreme location to increase the favorable effects of the tendons in the cross section. I will leave this dialog box with the OK button as well. Now I will open up the tendon geometry, and I will delete the already cloned tendons by right click on it and choose the erase option. Now we have deleted the cloned tendons and we only have the master tendon in the system. Now what I'm going to do is to clone the tendon again, but instead of just creating 2 duplicates or 2 cloned tendons, I will clone the tendon on every 150 millimeter to the right and to the left from the center until I reach the -900 millimeter and +900 millimeter on the left side and on the right side as well. So let me start it by simply right click on the tendon geometry axis and choose the clone, and then I will add here -0.150 millimeter and for the V offset 0 and click OK. I will click again with my right mouse button on the tendon geometry, choose the clone, and in this case I'm going to enter 0.150 millimeter with a plus sign and 0 and click OK. Now I have my first 2 cloned tendons. I will repeat this procedure many times, so clone -0.3 meter and 0, plus 0.3 meter and 0, Okay, so now I have cloned my tendons 12 times, so altogether I have 13 tendons in my system. I'm going to click on the Save button, and then I'm going to export the model. So I will click on the Export button and click OK. After having exported the model to the database, I'm going back to SST, and now I will right click on the SOFiPlus entry and choose the Calculate from SOFiPlus from the drop-down list. In this way, all the tasks below SOFiPlus will be recalculated. It took 77 seconds to recalculate all of the tasks, and as you can see from the analysis protocol, in this time I didn't get any warnings, so everything ran through without any errors and warnings. If you may remember previously, I had the warnings at the check print of the crack design. So it seems to be that our modifications were pointing in the right direction, and now the system will be adequate and a more economical design of the normal reinforcement is possible. Let's prove it by reviewing the stress plots in the report browser in the next video. In this video we are going to review the stress plots of the check print of selected elements task. Please right-click on the task and choose the Reports option. The report browser will be open for us and we can have a look at the stress plots. If we close back the AQB check print crack design and open up the first results entry, you will find the plot of the stresses in the combinations rare, frequent and permanent. If you click on this entry, first you will find an explanation about this chapter and how the plots are calculated. What is important from this message is that the following plots show linearly calculated section stresses. As I mentioned in my previous video, all of the stresses below will be presented and calculated in a linear manner, but this can be done if in the final SLS state the cross-section will remain in fully compression. If I click on the second entry line, I will find the stress plot of the G_1 plus the P. However, in this case I can see the pictures in one A4 size paper, 2 pictures per page, which is proper for the report at the final print. However, for review I suggest we should go to the Graphics tab and look at the stress plots there. So what we can see in this diagram is really a linear stress distribution within the cross-section. The red means compression and the blue means tension. And in the legend you can read which case the plot represents. For example, in this case, this is the summation of the stresses from the G_1 effect plus the pre-stress that had been stored in load case 1061. In beam element 200,017, which is in the middle of the first span, and the stress plot has been created at the beginning of the beam. Then the next picture shows the very same case, but for beam element 200,035, which is the beam at the middle support. Then we can see a plot about the overall G effects plus the pre-stress effects for beam 200,017, one for the beam element at the support, and then we can also review the G plus P plus C effects. As we can see, still there is a little bit of tension in the concrete, so if we want to undertake a real design of a real bridge, maybe we should further increase the number of the tendons or the number of the strands within the tendon. In a very similar fashion, the SLS rare check is presented, or I should say that the stresses from the SLS rare combination is presented in this picture for the beam element 200,017 and 35 respectively. As you can see, still we have a little bit of tension above the middle support in the SLS rare case, and also in the SLS permanent case. Then we can review the SLS cases, for example for the max MY bending moments and the min MY bending moments. for the first selected beam and also for the second selected beams. Max my and then the min my. Then we can also find the strength check in the ultimate limit state. In this stress plot, for example, for the beam element at the support, we can very nicely see the development of the stress in the concrete follows the ULS stress strain curve. And also what we can recognize is that when we define the cross-section and set up the non-effective area within the cross-section, we selected the rebars not to working within this non-effective area, and this picture is a very nice proof of it, since we can only find stress value in the rebars outside the non-effective area. So we can conclude that basically reviewing the stress plots will give you a very nice information and useful information about the stresses within your structure, and you will know if you need to interact and modify your structure in order to keep the stresses within the cross-section in the desired range. This basically concludes the overview of the check print of the selected beam elements task, and we are going to continue with the design of the beam elements in the system in the next video. In this video we are going to continue with the design of all the elements in the system. Please right click on the last task, CSM Bridge Design Check Print of Selected Elements, and choose from the drop-down list the Insert Task option. From the available task list, please select the CSM Bridge Design Beams and click on the OK button. Then I will rename this task by right-click on it and choose the rename. And I will add the new name Design of all beams in ULS. Then click outside. Now please select the Design of all beams in ULS and hit the Enter button, and the dialog box will be open. And on the first tab, the Checks tab, I would like you to tick in the ultimate limit state check, and on the second tab, on the Check Print tab, I would like you to deselect the check print and then click on the OK button. If you do so, the analysis will start and it will be finished in 5 seconds, and as you can see we received a warning message which we should look at. If I go to the calculation protocol and scroll up a little bit, I will find this warning message stating that shear design is not possible for 8 cuts. I will open now WinGraph to have a look at these locations. After having opened WinGraph from SSD, I went to the design of beam elements and the design of the beam elements, where I can have a look at the longitudinal reinforcement layers but also the stirrup reinforcement layer. However, if I click on the stirrup reinforcement layer 2, I can see marked with red color the problematic beam elements and also the text which says that the sigma 2 value of the concrete is exceeded. The sigma 2 value is the compression limit stress of the concrete, and since it is exceeded, the shear design is not adequate for these elements. If we look at now the stirrup reinforcement layer 3, we will find also the very same beam elements being problematic. The stirrup reinforcement layer 2 and 3 were defined in the shear cuts of the flange within the cross-section. For those kind of shear cuts, the methodology for the shear design in the cracked cross-section is based on the difference of the longitudinal forces for the flanges. However, if we want, we can control the shear design procedure, and with the help of a text input, we can switch to a shear design that is based on the sectional values. So this is exactly what we are going to do. We are going back to SSD now, and I will change the design of all beams in ULS state task into a text task by right-clicking on it and choose the Convert to User Task option. In this way, the task will be converted to a text task, and if I double-click on it, it will be available for me for free editing. As you can see, the design of the beam elements in the ULS state happens in module CSM, and since we have the superpositioning of the load cases, the only command we need to add is design in the ultimate state of the beams. So it is DAISY ULTI E-type beam. If we want, in the CSM module, we can also control the underlying AQB run. It is possible with the command control AQB text. Between the apostrophes, I can specify another command that is valid in module AQB. In the description of the AQB module, at the command control, which command controls the calculation, we will find the parameter DESV, which controls the shear design methodology. If you click on this parameter, the PDF editor will jump right to the explanation of this parameter. The default value of this control DESV command is number 1, shear from the difference of longitudinal forces for flanges. However, if we add the command control DESV0, then shear will be performed on the sectional values. Let's go back to SSD and add this command line. So now I just simply need to add the command control DESV0, and basically what we are doing, we are controlling the AQB with the text, and in this text the command is control DESV0, which is a valid command in module AQB. If now we run the design of all beam in ULS state with this given input, hopefully the warning messages will disappear. So just right click on the design of all beams in ULS state task and choose the calculate. If you do so, the analysis will run through, and really we didn't receive any error messages or warning messages in this case. If we go back to WinGraph and check the stirrup reinforcement layer number 2 once more, we can see that the problematic beam elements disappeared from the system. Also, if we look at the stirrup reinforcement layer number 3, we will find that everything is proper. I'd like to talk a little bit more about the background of this warning message. I remained in WinGraph, and at the moment I'm presenting to you the MY bending moment diagram, the minimum MY bending moment diagram in the ULS case. The problem is that we have quite a high value above the support, but also the rundown of the diagram is very steep. Especially if we consider one beam element, the MY bending moment at the beginning and at the end of the beam element is quite different. That makes the design of the necessary amount of reinforcement very difficult. The way how we can help module AQB to assess the necessary amount of reinforcement is to decrease this peak value and also to make this diagram a little bit shallower. The way how we can achieve this is that we try to match the geometry of the tendon the best we can to the rundown of the most critical MY bending moment diagram. This is exactly what I try to do now. I will go back to SOFiPlus and I will modify the geometry of the duct. So I will simply go back to SSD, double click on the SOFiPlus, and then in SOFiPlus I'm going to revise the geometry of the tendon. To do that, I will click on the Pre-Stressings tab, right click on the tendon geometry and choose the Edit with PT Editor option. On the Edit Geometry tab, you have the possibility to modify the geometry of the duct. I will select the geometry point that corresponds to the middle support, which is at span station 2.0, and I will add the vertical radius with 4.3 meter, which is the minimum amount for this particular duct, and then the influence length of this radius will be set to 1 meter. Then I will click outside, and please notice how the geometry at this location will change. So as you can see, the geometry of the duct became more steep to match more with the geometry of the bending moment diagram. Now I will click OK, export the model and rerun the analysis. So I will click on the export button, then on the OK button. After having exported the model to the database, I will simply select the SOFiPlus task. I'm going to right click on it and choose the Calculate From option. The analysis has been finished in 82 seconds. Let's go back to WinGraph and see how the bending moment diagram changed. I will simply select the yes, and as you can see, the minimum my bending moment dropped significantly. The value of my decreased more than 4,000 kN/meter. As you might realize by now, sometimes it is not so easy to assess or to obtain the necessary amount of reinforcement. In some cases like this, you might need to fine-tune your model by adding some extra tendons or changing the geometry of the tendon, or using some extra controlling option in the design procedure. Now let's go back to SSD and review the output of the design of the beams in the ULS state. In SSD, you just need to simply right-click on the design of all beams in ULS and choose the Reports option, and the report browser will be open. On the second tab, which is called Graphics, we are going to find two pictures. The first picture contains 3 diagrams. Maybe I will start to explain the bottommost diagram that represents reinforcement layer number 2 in design case 11. This design case 11 was created to store the necessary amount of reinforcement in layer 2 in the ULS checks of the beam. And the diagram shows that the 45.6 cm² minimum amount of reinforcement was adequate along the whole superstructure for the ULS case. In the middle diagram, we can see the necessary amount of reinforcement in layer 1 that had been stored again in design case 11 for the ULS case. The 28.1 cm² minimum amount of reinforcement was adequate almost everywhere along the superstructure, except at the support and its close vicinity. However, as I mentioned previously, at this location where the my bending moment changes so drastically and in a so steep way, sometimes module AQB has difficulties to find the equilibrium in the cross-section. Therefore, these presented values should be treated with caution. Maybe a double check by a hand calculation is reasonable in this case to verify the calculated or obtained reinforcement at this area. Finally, the topmost diagram presents the sum of layer 2 and layer 1. That is why we see the slight increase around the middle support. The second picture shows the shear reinforcement in layer number 1, shear reinforcement layer number 1. If we click on the first Result tab, we are going to find an overview about the design task. We are going to have some information about the used code, the reinforcement distribution, the necessary amount of reinforcement will be stored, and also some information about how we can access the results in WinGraph. The AQB chapter is very similar to the ones that we already looked at, so I don't think I need to explain anything here. That concludes the video about the design check of the beam elements in the ULS state. And in the next video I'm going to continue with the crack width check of the beam elements in the SLS state. In this video I'm going to show you how to undertake the crack width check of the beam elements in the SLS state. All we need to do is again right-click on the very last task and choose the Insert Task option. From the Insert New Task dialog box, choose again the CSM Bridge Design Beams and click on the OK button. I will rename this task as well. Right-click and choose the rename. And I will enter Crack with Check All Beams. Hit the Enter once more. And in the dialog box I will simply select the Crack control. And I will also select the Crack With checkbox and leave the default value of the 0.20 mm in the box. On the second Check Print tab, I will deselect the Check Print and then I will simply click on the OK button. Then the analysis starts. After 5 seconds the analysis has been finished and we can read that module AQB performed the crack design and the minimum reinforcement check. Let's have a look at the report browser output of this task by right-clicking on it and choosing the reports. If we look at the first chapter, CSM Crack with Check for All Beams, and click on the Overview Design Task Beam Elements, we can read a very nice overview about the design task. Basically, in this design we checked the minimum reinforcement according to the Eurocode 1992-2, chapter 7.3.2, the increased reinforcement, if there is any, stored in design case 12. Also, we have undertaken a check of the crack width from the frequent combination rule according to EN 1992-2, chapter 7.3.4. The reinforcement was stored in design case 12, and the results for representation in WinGraph is stored in load case 9393. Finally, the task enveloped the necessary amount of reinforcement and stored it in design case number 1. Then in the second overview table we can read more information about the result of the beam elements. Apart from the stored design case, we can read that the maximum utilization of all AQB combinations was smaller than 1, and hence the crack design or the crack with check was not decisive. If we click on the second tab, the Graphics tab, we will see the utilization level of the SLS crack with check, which is assessed for the longitudinal reinforcement and stored in design case 9397. What we need to realize in the picture is that the utilization level is below 1.0 all along the superstructure, which means that the normal reinforcement hadn't been increased. The software will only increase the reinforcement due to the crack width check if the presented utilization level is greater than 1.0. This also means if we now click on the first graphics, we will find 3 pictures that present the longitudinal reinforcement of the beam. And of course these pictures are exactly the same what we saw at the ULS check, since the software didn't need to increase the reinforcement due to the crack width check. This is the way how you can perform a crack width check for the beam elements in your system. Now let me present the next check of the beam elements in the next video. In this video I'm going to show you how to perform the next check of the beam, which is the stress limitation. Again, we need to insert a new task, choosing it from the Insert New Task dialog box, selecting the CSM Bridge Design Beams again and click on the OK button. As usual, I'm going to rename this task, and the name will be Stress Limitation of All Beams. I will hit Enter 1 time and 2 times. Then I will select the Stress Limitation checkbox, and we can read what type of checks will be undertaken in this calculation. Chapter 7.2 and 7.2.5 will be performed. Then a linear stress check under the quasi-permanent combination for the concrete and the pre-stressing steel according to the quoted chapters. Finally, a nonlinear stress check under the quasi-permanent and characteristic order, a rare combination for pre-stressing steel, will be performed. Now let's click on the Check Print tab and uncheck the Check Print checkbox. Then let's go back to the Checks tab. Okay, let's click on the OK button and review the results in the report browser. Before we click on the OK button, go to the Check Print tab and take out the Check Print selection and then click on the OK button. In the analysis protocol, we can see that module AQB performed a stress check first under the characteristic combination for the concrete and the steel materials. Then it performed the linear stress check according to the quasi-permanent combination rule for the concrete and the tendon steel material. Then came two nonlinear stress checks for the tendon materials in the quasi-permanent combination, and another one for the tendon in the characteristic rare combination on the cracked section. Let's review the output of the task in Report Browser by clicking on the task and choosing the reports. And again, maybe the best is if we start with the pictures to overview the pictures. I'm just going to zoom out a little bit with my mouse. Okay, so this diagram shows the stress in the concrete from the characteristic or rare combination. You can see again the inferior and superior, which refers to the 90% of the pre-stress and 110% of the pre-stress. And so the stresses in the concrete should be smaller than 0.6 times the FCK. And in brackets we can see this value being calculated and equal with 24 Newton per millimeter square. This is basically a visual check. You need to overview your superstructure and see if the stresses are higher than the limiting 24 megapascal. As you can see in the middle area, so at the middle support, the stress is quite higher than the allowable limit. In this case, the user needs to interact. So it is important to mention here that the reinforcement is not increased due to this check. The software simply calculates the stresses in the concrete and represents it for you in a diagram, and you need to decide how to avoid this exceedance in the stress of the concrete. Now we can review the second picture, which is about the nonlinear steel stresses in the reinforcing steel from the characteristic rare combination. And from this combination, the reinforcing steel shouldn't get higher stresses than 400 megapascal. As you can see, our structure is problematic again at the middle support. So the user needs to do some interaction and change the model at this location to fulfill the nonlinear steel stress check of the reinforcement. Let's click now on the third picture, or I should say the third graphics. And in this graphics, in the first picture, we can see the concrete stress from the permanent combination in SUP once more. And according to this check, the linear stresses of the concrete should be smaller than 0.45 times the FCK value in the top fiber of the reinforcement from a uniaxial check. Here we can see two diagrams. The first one is showing the concrete stress in the top fiber from the max MY, whereas the second one is showing the concrete stress in the top fiber from the minimum MY bending moment. This check needs to be undertaken since there is a chapter in Eurocode that the creep and shrinkage effects can be considered in a linear way if the linear stresses of the concrete is smaller than 0.45 times the FCK value. This check is fulfilled since the 0.45 times the FCK value is equal with 18 megapascal. At least it is fulfilled for the top fiber of the cross section. Let's have a look at the results in the second picture, the middle picture, which shows the bottommost fiber of the cross section, again from the maximum MY and minimum MY combination. And what we can conclude is that in the first span the stress is 16.5 megapascal, so it is adequate. In the second span I can see the maximum value being equal with 18.6 megapascal, which is slightly exceeding the limiting value, and again refers to the fact that the user might need to do some interaction to make the structure adequate. The third picture shows the maximum biaxial stress in the concrete, which should be also smaller than 80 megapascal. And in this picture we can see again an exceedance of the stresses. In the first span we can see 22.3 megapascal, at the support 23.2, and in the second span something like 25 megapascal. So unfortunately this check hasn't been fulfilled successfully. The user needs to strengthen the structure somehow. Now let's review the next graphics. This graphic is only presented for information, so the values in this picture are not compared with any limiting value. In these two pictures, the inferior and the superior values of the maximum tendon stresses are presented in the permanent combination. So in the top picture, 101% times the mean value of the pre-stress is presented, and in the bottom picture, the 90% of the mean pre-stress value is presented. Here you can read that this picture is for information only, and also another information about why the stresses are higher than the calculated ones with the average pre-stress values. So I think we can jump to the next graphics, in which the first picture shows the tendon stress in the permanent combination with the mean value of the pre-stress in the tendon, and according to chapter 7.2.5 the stresses should be smaller than 0.65 times the FBK value, which is 1020 megapascal in this case. As you can see, this check is fulfilled, everything is alright here. In the bottom picture we can see the minimum stress in the tendon. Since the top one was presenting the maximum stress in the tendon, you can see that the two values are very similar to each other. Basically we used a lot of tendons, and of course the stresses within the cross section is not constant. Therefore there will be a slight change in the stress of the tendons, and therefore there will be a maximum stress in the tendon and a minimum stress in the tendon. The minimum value is also smaller than the limiting value, so everything is fine with the minimum value as well. Let's review the last graphics, which again shows the tendon stresses, the maximum and the minimum one in the characteristic combination on the cracked section, and according to EN 1992-1-1 chapter 7.2.5 the mean value of the tendon should be smaller than 0.75 times the FBK value, which in this case is 1170 megapascal. And as you can see, for the maximum value and for the minimum value of the tendons, this check is also fulfilled. After having reviewed all the graphics on the Graphics tab, let's go back to the Results tab, collapse all the chapters by right-clicking on the first one and choose the Collapse All from the drop-down list. Then open up the chapters one by one. So I will click first and open the CSM Stress Limitation of All Beams chapter and choose the Overview Design Task Beam Elements subchapter. Because here I would like to show you that you can find an overview about the design task of the beam elements. All the chapters are presented according to the design checks will be performed. Also you can see the design case numbers that the results will be stored, and if you scroll down the page a little bit you will find a more detailed overview about the results of the beam elements. Then it is worth to open up the AQB checks Since the results can be overviewed not just in a graphical format on the Graphics tab, but also in a table format in this Results tab. So if we, for example, open up the first AQB chapter, which is about the stress check, and choose the very last entry, which is the maximum stresses and checked limits, then we will find the same what we saw in the pictures. That, for example, in material 1, in the concrete material, the longitudinal compressive stress of the concrete has been exceeded. Since the limiting value is only minus 24 megapascal, but there is minus 32.7 megapascal in beam element 200,034, which gives us a utilization level of 1.36. Similarly, we will find that the reinforcing steel material number 2 is also problematic. The longitudinal tensile stress of the reinforcing steel has been exceeded, since the limiting value is 400 megapascal, but the actual one is 485 megapascal. Again, the problem is at beam 200,034, and the utilization level is equal with 1.21. The table type of representation can give you a good clue where you need to interact to your structure and how to change the model to fulfill these checks. If we open up the next AQB run result and choose the elastic stress check, again we will find the stresses marked by red that are over the limiting value. For example, in material number 1, so again in the concrete, the maximum compressive strength is minus 25.04 megapascal, which is higher than the limiting value of minus 23.28. Also, we can find, for example, that in the pre-stressing steel material number 4, the stress range, so the delta sigma, is a little bit too high. The difference between the minimum sigma and the maximum sigma stresses in the tendon is 373 megapascal. Then in the below table, again we can find the non-conforming value marked by red again, but in this case the utilization is being presented. In a similar way, we can overview all the AQB checks and click and see the maximum stresses and check limits, also from the last AQB runs. However, there is also another possible way to do that, namely, if you go back to the very beginning of this output, choose for example the first entry, and in the toolbar we can find an icon which is for to search the document and find the critical limits. If you click on it, the document will automatically jump to the location where the stress limit has been exceeded, and if you continue clicking, all the values will be presented where the limitation hasn't been fulfilled. So this could be another useful way, for example, to go through your document and find the values that are not fulfilling the limitations or the checks. That concludes the overview of the stress limitation of all the beams in the system, and now let's continue with the next check of the beams in the next video. In this video I'm going to show you how to perform the decompression check of all the beam elements in your system. All you need to do is right click on the lastly inserted stress limitation of all beams task, and from the drop down menu choose the insert task. From the prop up dialog box we should choose the CSM Bridge Design Beams and then click on the OK button. Then the new task will be inserted, which I'm going to rename it by right click on it and choose the rename option. I will enter a new name, which will be the decompression check, and then I will hit enter 2 times, once and once more, and then I will be directed to the decompression check task. I will choose the check to be performed, decompression check, and below we are going to receive some information about the check to be performed. First, the decompression check under the quasi-permanent combination will be performed according to chapter 7.3.1. Then, as a second check, the concrete edge stresses will be shown for you only as an information from the quasi-permanent combination according to, again, the chapter 7.3.1. Please select the Check Print tab and unselect the Check Print selection box, and then please click on the OK button. The analysis or the check will be performed, and now we can review the results by right-click on the task and choose the reports. Again, maybe the best practice would be to go to the graphics and have a look at the pictures or the graphics. Let's choose the third graphic and review the pictures in it. In the topmost picture, we can receive as information only a linearly calculated stress within the cross-section at the top fiber of the cross-section in the decompression check from the permanent combination rule. And this picture presents two diagrams, the load case 9490 and 91, received from the max MY and min MY case. And the diagram shows that in the concrete we have compression along the whole superstructure except at one location. In the middle of the second span we can see from either load case 9490 or 91 a little bit of tension. The middle picture presents the bottom fiber of the cross section, and as we can see here we have a little bit of problem over the middle support because the concrete gets 4.52 megapascal tension, which of course should be avoided by revising the model and introducing more pre-stress into the system. Both the top and the middle picture was calculated based on uniaxial loading. And now let me talk a little bit about the bottom picture. This picture presents the maximum tensile stress in the concrete from a biaxial loading, and one should think for the first blink that basically this diagram presents the maximum value of the top two diagrams. However, this is not exactly the case, as you can see, because this check is undertaken according to the German National Annex of the Eurocode, which prescribes for the design engineers to prove that no tensile stresses may occur under the decisive action combination at the edge of the cross-section which is closest to the tendon. And the phrasing closest to the tendon is not quite clear sometimes. Let me explain it in a small example. Occurring in the cross-section, we need to go back to WinGraph and find the element, the beam element. So I will go back to SSD and go for graphics. And in graphics I am presenting now the design of the beam element, the stress of the materials and the maximum tensile stress of the concrete. And we can find this value here in the middle of the first pan, 1.07 megapascal. And if we zoom in a little bit, I'm also presenting the number of the beam elements. So in the cross section of beam element 200,013 we are going to find this 1.07 megapascal. Now let's go back to SSD and open up the result viewer and search for this beam element. The way how you can work in the result viewer is going to be explained later on in the course. I have simply selected the beam element 200,013 and I am presenting the cross section at x equals 0.807 meter, and we are looking at the result of load case 9492. And actually I'm presenting the reinforcement steel stress and axial material stress in the cross section. However, as you can see, there is no value to be shown. Why is that? It is because the design case 9492 is an envelope case. This means that the diagram shows the maximum value of the decompression check in the cross-section, and therefore it is also not possible to show it in one cross-section. Since it's an envelope, it is not possible to present it in one cross-section. So if we want to check that the decompression stress in the concrete along the edge that is closest to the tendon is not greater than 0 megapascal, then we should review load case 9490 and 9491 in the result viewer. So if in the result viewer I'm presenting the 9490, we can now really see the stresses in the cross section, and the edges closest to the tendon will be the following three edges: the right vertical one, the horizontal bottom one, and the left vertical one. If we look at the stress values along these edges, we can see that everywhere there is compression in the concrete, so the check is fulfilled. If we now select the next load case, 9491, we can see tension in the cross section along the topmost fiber. However, the check is still fulfilled, since along the closest edges to the tendon, the decompression stress in the concrete is still compression everywhere. So this is what I wanted to explain about the bottommost picture, that it is an envelope one, and you really need to go into detail and look at or review the stresses in the concrete in the cross section. Now let's click on the middle graphic and have a look at the picture. In this picture we can see three layers. All of the layers are presenting the maximum nonlinear strain at check distance above and below the duct. The strains needs to be negative, which means everything is under pressure and the check is fulfilled. And the three layers that are presented is design case 9495, which has been received from the maximum MY combination, then design case 9496, and finally the envelope of the first two, 9497, which is simply called max. And if we click on the first graphic, we are going to see the max nonlinear strains at check distance above and below the duct, and only the envelope case, the 9497, is presented. This concludes the video about the decompression check of the beam elements, and I'm going to continue with the next check in the next video. In this video I'm going to show you how to perform the stress range check of all the beam elements in the system, and in this time I'm going to show you a different approach how to insert the necessary design check task and select the copy task option from the drop-down list. Then once more use your right mouse button and right click on the copied task and choose the rename option. I will rename the task to the stress range check. And then open the task by double clicking on it. The dialog box will appear and I will deselect the decompression check and select the stress range check. Now let's review together the checks to be undertaken. First, a special check according to a German special report will be undertaken, considering only 75% of the pre-stress for the couplings. Then a simplified stress range check from load model number 1 without the temperature and the settlement actions under the frequent combination rule, considering the pK inferior, will be considered according to Eurocode 1992-1-1. If we had defined action FAT, then the CSM bridge design task is capable of undertake the damage equivalent stress range check for steel and concrete according to Eurocode 1992-1-1, chapter 6.8.53 and 6.8.7. However, in this example 5 we do not have action FAT, so fatigue, but I'm going to give you some explanations and instructions how to perform this type of check. Now just simply click on the OK button and wait for the results. It took a little bit longer than the previous checks, but now we can open up the report by right-clicking on the task and choosing the reports from the drop-down list. And as usual, go to the graphics tab and go through the graphics. Maybe it is necessary to zoom out a little bit by using your middle mouse button. As we can read in the first picture, this is a fatigue check for the welded connections and the tendon couplings. Basically, this is a graphical overview of the stresses in the concrete, for which the whole concrete cross-section should be under compression at 0.75 times the pre-stress. So basically we need to review our superstructure, and of course we should know where the couplings or the welded connections of the tendons are, and we need to be sure that the concrete is in total compression at the location of the couplings or at the welded connections. As we can see in the first picture, this check should be fulfilled since we can see compression all along the superstructure. So irrelevant where the couplings or the welded connections are, the full concrete cross-section is in compression. However, in the second picture we can see that at some portion of the superstructure, the uniaxial bottom stress of the concrete goes into tension. So we need to make sure that there is no couplings or welded connections at this location, or if there is any, then we need to revise our model, and we might need to increase the number of the tendons to fulfill the criteria of the cross-section being in compression when only 75% of the pre-stress is applied. In the forthcoming pictures, we can see stress plots of the cross-section found at beam element 200,017-35 from the calculated max MY and min MY cases. So if you know exactly where your couplings or weldings are along the tendons, then all you need to do is specify the beam element number in this check and review the stress distribution diagrams of these cross-section, because there could be a case, such as it is presented in this picture, that although we have tension within the cross-section, but it is located at the topmost fiber of the cross-section where there is no tendon or connection or joint of the tendon at all. And we might accept this situation since we can say that where the tendons and their joints are located, the cross-section is in compression. In the next picture we are going to overview the next check. What we are reviewing in this picture is the longitudinal stress sway of the reinforcement in the cross-section, which should be smaller always than 70 megapascal. In the picture one can see several lines, and these lines show the stress range of another temperature and settlement combinations. So basically in the preceding maxima runs where we created our superpositionings, we had set up a special combination where we combine only the temperature and the settlement effects, and the software had calculated the envelope for the max-min normal force, for the max-min My bending moment, for the max-min VZ shear force. And now we are using those combinations here to get or to assess the stress in the longitudinal reinforcement. Plus, or in addition to this, we also add the action of the traffic, However, they are considered with a factor of 1.0 in this stress range lines. So this diagram is just showing you the different lines or diagrams, but it doesn't give you any values. And as you can see, most of our superstructure is fine. The check can be fulfilled with the current system. However, again, at the vicinity of the support, we need to undertake some remedies to lower down the stress in the longitudinal reinforcement. The similar pictures can be seen, and the similar check was undertaken for the shear reinforcement in our cross sections. In this picture, we can see the different stress ranges from the different temperature and settlement combinations. And in the next picture, we can see the envelope. And of course, here it should be fulfilled that the stress within the shear reinforcement is always smaller than 70 megapascal. However, as you can see, this is not the case. This is normal, I should say, for the shear reinforcement in the system. And in these cases, what we can do is undertake a different type of check, namely the damage equivalent stress range check for load model LM3. And this type of other approach I would like to show you in the next video. In this video, I would like to introduce to you a new fatigue check approach, namely the damage equivalent stress range check for load model LM3. The best way I can do that is with the help of a text-based input with TEDdy. So I would like you to open TEDdy 2020 and then go to the File menu and choose the examples. If you do so, the example folder will be opened for you, and here you need to open up the CSM folder, then you need to also open up the English folder, then you need to open up the design subfolder and choose the file that is called csm_design.dot. When you double click on it, it's going to be open. Now we can close back this example tab or taskbar, and we need to store this file somewhere in our computer. So I'm going to go back to the File menu and choose the Save As option. And then I'm going to select my desktop and then the Print-SLS Bridge folder, and here I'm going to create a new folder with the name of CSM_31 and enter, and I will store the file within it by clicking on the Save button. Once you've done it, you are able to run the file. But first, let's overview what is inside of this file. On the left side, we can see the module names and a little bit of description about all the modules that they are doing. First, in module Aqua, we are selecting the code. Then we set up the materials, concrete and steel, and we define our cross sections. If we scroll a little bit down, we will find module SOFiMesh A, where we are defining our model. First, we set up the nodes, and then we are creating the beam elements. So basically, we are creating the finite elements directly. Then we are creating the result sets in the forthcoming SOFiMesh A module. In module SOFiMesh C, after the last SOFiMesh A module, we are setting up the one and only axis in our system. Then in module SOFiLoad, we are defining the actions within our system. With the help of command action, we set up G_1, 2, P, C, L_T, and U. By now, these type of actions are familiar to you. Then if we scroll down, we will find the definition of the tendons in the system. Further, if we're going down, we can see the single load cases such as load case 1, 2, 3, and so on and so forth. Then in the next module ASE, we are analyzing these load cases.
Here I would like to point out that load cases from 701 till 718 were created with the load train LM3 for this fatigue check. And then the linear analysis, we can find the CSM. First, the normal CSM run, in which we consider the installation of the model parts and then the creep and shrinkage effects until time infinite. So this is the place when the GPC actions and load cases are created. Then you can also find the check prints, as we did in our example file as well. Right after the normal CSM run, we undertake a check print. Then the superpositioning, the pre-superpositioning with the variable actions, as we did in our example file as well. We pre-superimpose the variable actions, for example, L_U, L_1, T, the settlements. And with the help of Daisy Mux, we create the pre-superpositioning. Again, then after this CSM pre-superpositioning, we undertake a check print, like we did in our example file as well. If we further scroll down, then we will find the first ultimate design check of the beam elements in the system with the help of command Daisy Ulti. Then after the ULS check, we undertake some SLS checks, such as the minimum reinforcement and crack design for all of the beams. Then the stress checks, then the decompression check. And finally, we reach the point in the input where we undertake the fatigue check with damage equivalent stress range for load with model LM3. If you have a closer look at the input, you can see that basically we trigger the command Daisy Fat with some parameters. Basically, with these parameters, we can narrow down the stress range check to be verified or to be used from the previous maxima runs. As you can see, for example, parameter 1 set to 4 will only use the maximum and minimum My and maximum and minimum VZ shear forces obtained from the permanent combinations of the temperature and settlement actions. Similarly, the parameter 8 value 2 will mean that only the maximum and minimum My bending moment cases will be used to evaluate the stress range for the fatigue loads. Then with the help of command lambda, you need to specify some special parameters. And the special parameters are for the lambda values. If we now go back to SSD and click on the stress range check task, we can see these lambda values as well. If we check the damage equivalent factors checkbox, we can input a lambda value for the reinforcing steel in span, and other lambda value for the shear reinforcement in span, and a third lambda value for the pre-stressing steel in span. Exactly the same option we have for the inner supports, for the reinforcing steel, for the shear reinforcement, and for the pre-stressing steel. Finally, we can define a lambda value for the concrete material. The corresponding text-based input can be seen on the screen now, where parameter LMS is the lambda value for the longitudinal reinforcement in midspan, parameter LMS2 at the inner supports, lam_t is the lambda value for the tendons in the midspan, LMT2 is the lambda value for the tendons at inner supports, parameter lam_l is the lambda value of the shear links in midspan, and the parameter LML2 is the lambda value for the shear links at the inner supports. Finally, lam_c is the lambda value of the concrete material. We can also see, if we run this file, project name _FAT file will be created and applied. So now I would like you to calculate this file until this +apply input line. So basically I'm going to right click on this template and choose the minus sign from the cursor position, and then I will go up and click on the calculation. So basically I'm going to right click on the template and choose the minus from cursor position, and all the unnecessary tasks after this apply input line will not be calculated. And now I will simply just click on the immediately button and all the tasks will be performed, and we are going to be able to review this project name underscore fat.dot file. After having run through the analysis successfully, you can come back to the TEDdy input and click on the Explorer icon in the Home ribbon, and then File Explorer will be opened, and now we can open up this FAT dot, so CSM 31 underscore design underscore FAT dot. I will double click on it, and it opened in a TEDdy environment, so we can read through the input of this FAT dot file. Without going into very detailed explanations, I'm just going to call your attention that first you are going to find and you can read through a template about the whole procedure. First, just general about the design concept. Then we can see that the fatigue check at the couplings is undertaken. Then the fatigue of the reinforcement stress strain check, so the simplified stress strain check, has been undertaken. And then we reach the chapter we are most interested in, the design concept fatigue with damage equivalent stress range for load model LM3. And if I click on it, here we can see and read through a template about the damage equivalent stress range check with LM3. Without going into details, I'm just going to explain that basically it has three main parts. The first part is an AQB run in which the axial load of load model LM3 factorized by 1.4 is considered, and all the beam elements has been checked, and the reinforcement is increased if the fatigue check has not been fulfilled. Then in the second step, which is also an AQB run, a stress range check of the concrete will be performed. In this check, the increased reinforcement will be considered in the concrete cross-section, and the load factor for the axial load will be 1.0. Finally, in the last step, which is also an AQB run, the design of the support regions will be undertaken, in which the axial load factor is going to be 1.75 for all of the elements, and also the increased reinforcement will be considered in the cross sections. Last but not least, the user has to decide if a beam must be assigned to a span or a support region, and whether the first or the third design case was the decisive one. Of course, the aforementioned design approach can be activated graphically as well. I just wanted to give you a brief overview about how this approach is working. So if I go back to SSD, for example, and double click on the stress range check, as you can see here, I can also activate the very same approach. The only prerequisite I need to be able to undertake this approach is to define action FAT, the fatigue action, and to incorporate load model LM3 in the traffic loader task. But apart from these prerequisites, the application of the damage equivalent stress range check is also possible with a graphical way, as you can see.
In this video, I would like to go through together with you the input of the design of all beams in ULS state task. After having double-click on the task, you might remember that we already input one line together into this task, namely when we controlled the AQB run, the underlying AQB run. And this is exactly what I would like to show to you What is this underlying AQB run and what is its content exactly? As you can see in this input, the content is stored in the project name underscore 39 dot dot in the project folder. So if I click on the Home ribbon and click on the Explorer, and I will be directed to the project folder, and I just need to double click on the ptc underscore bridge underscore 39 dot dot file. And the data will be opened with the help of TEDdy 2020. What we can see in the very first line, a command hash defined project equals ptc underscore bridge. Since it is a standalone dot file, so in other words, we are defining the project to be equal with the ptc underscore bridge.cdb. This also means that, for example, when we undertake the ULS check in the first AQB round, the software will know that it needs to perform the commands on the ptc underscore bridge.cdb file. After the template which introduces the design concept, we will find the first AQB input. As always, the commands are between the head and the end command lines. Then we are going to find some echo lines which are setting the output in the report browser, followed by some control input lines in which first we take into account the reinforcement for the creep and shrinkage effects, and we are also taking into account the change of the normal force when we are performing the normal bending design. Then we can see the command line control DESV equals 0, which is due to our previous input in SSD. In SSD, we control the run or the procedure of module AQB with the command line control AQB text control DESV0, and this means that this line control DESV0 will be inserted in the AQB run, and this is exactly what we found in module AQB. Then with the command rein LCR11 rmod sing, we are going to store the reinforcement obtained from this ultimate limit state design. So basically we are storing the reinforcement in design case 11, and it's going to be visible for us, for example, in WinGraph for representation. Then we need to select the beams to be checked, and we are doing it with the help of command beam, group all, construction stages auto. This input line means that I'm going to select all of the beams in all of the groups for a check. Then we need to select the load cases to be used in the design. This can be done with the help of command LC, load case. Then we use a special input. The first character will be the first number of the load case, and with the question mark, we refer to the remaining 3 digits, and this will mean that all the load cases starting with digit 5 will be selected. Similarly, all the 6,000 load cases, 15,000 load cases and 16,000 load cases will be selected in the check, or should I say for the check. Then we also select all of the load cases from the pre-superpositioning that had been stored in action y_d, or I can also say in the container y_d. The parameter CST9998 means that these load cases are acting in the final construction stage or after the final construction stage, when the cross-section reached its final status and it's not going to change, and the reference point of the stored internal forces and moments is the gross cross-section. Then we can see the setup of the combinations with the help of command comb. This is the most important point in our input, because now we are combining together the effects from action G, P and C together with the pre-superimposed action Y underscore D. At the location of the first parameter, which is extrema, you can find max, but also the letter D. If we scroll down the explanation table, you will find these shortenings: max D, min D, mam D. For example, the max D means that the ultimate design combination, the favorable and unfavorable, will be undertaken, and the action G will be multiplied with the unfavorable safety factor for the ultimate limit state design. Similarly, for action P, the unfavorable safety factor will be taken from the ultimate limit state design combination, and also the favorable unfavorable safety factor of action C, the creep, will be taken from the ultimate limit state design combination rule. If you see in the input max A, then it means that the accidental design combination rule and the corresponding favorable unfavorable safety factors will be used for the actions G, P and C. If you see, for example, max R or min R, then the characteristic combination rule will be used and the corresponding favorable and unfavorable safety factors will be used for action GPC, and so on and so forth. I think you get the hang of it. So now back to the combination line. We are combining together again actions GPC together with the pre-superimposed actions Y underscore D, and we would like to get the maximum and minimum MY bending moment in all of the beam elements. Since we are combining together internal forces and stresses in this case, it is not possible to use any other type of modules. Because one should ask here, okay, but why we are not combining together all these things in module maxima? The answer is because module maxima is only capable of combining together the results on the finer cross-section, but it is not capable of handling the change of the cross-section and combine together the internal forces of the cross-sections. I have already explained this in detail in the video in which I was talking about the concept of the CSM design approach. It is also worth mentioning that for the maximum and minimum MY combination, we store the results in load case 2105 and 06. However, for the other combinations such as maximum and minimum vertical shear force or torsional bending moment or normal force, we do not set up a special storing load case, but it doesn't mean that we are not taking them into consideration. It only means that we are not storing them in a result load case. And the reason behind is that finally we create a final envelope diagram with the help of command line comb gmax and gmin and load case store in load case 2107 and 2108. So basically with these two command lines we are creating an envelope of all the previous combination with the, from this AQB run. And when we have the envelope of the combinations, we can simply perform a DAISY or design check in the ultimate case. I think now we can close back the online hub. Basically all of the design checks that we did together in the SSD environment, the only change or difference what you will see if you look at the input of those design checks is that the selected load cases will be a little bit different. Instead of LCY underscore D, they are going to include or incorporate different type of actions such as Y underscore 1, Y underscore 2, 3, 4, and so on and so forth. And also the combinations will be set up differently. Instead of comb max D, you are going to find comb max R or comb max P. Let me show you this quickly. For example, if I click on the open button and instead of the PTC_bridge_39 dot, which is open at the moment, we open the PTC_bridge_41 dot, which opened on my other screen. So basically we will find here the crack design and the minimum reinforcement check. And as we can see, it's also undertaken in module AQB. And as I promised, the input is very similar, some echo option, the same control options. And then we will find now the command lines rein 2 times. And we are going to enhance the reinforcement and store the new amount in designed case 12. Then we will find the same beam command line. At the selection of the load cases, we will again find load case 5000, 6000, 15000, 16000. And we will also find all of the pre-superimposed containers, such as Y_1, 3, 4, 8, 9, Y_D and G. However, for this particular crack width check, by the way, the LC type Y_1 selection would be sufficient. But to be sure, or to make sure, the software selects all of the pre-superimposed containers. Then if we scroll down, again we are going to find the creation of the combinations. But this time, as you can see, instead of max D, min D and Y, we can find max R, min R input. And from these 4 letters, the software will know what safety factors to be used for actions G, P and C. The factors of the pre-superimposed container Y_1 is already included. And the other difference that you can see is that instead of DAISY ulti, so the ultimate limit state design, now we can find the command STRE, which stands for stresses, E for elastic, and the combination of letter E and RL is. So as you can see, in all of the design checks, the input procedure or the input structure is very similar. So with this little bit of information, you will be able to understand all of the underlying input of the graphical design tasks. All you need to do is go back to SSD, select one of the design tasks, right-click on it and choose the text editor option. And you can read the name of the file in the command line control file, in this case for example 46. So from this you can be sure that a project name _46 ... will be created for the decompression check. All you need to do is go back to the project folder and open this .file. This concludes the chapter of the CSM design procedure, and I'm going to continue with the explanation or with the introduction of the modules that are responsible for representing our results.